Plate tectonic boundaries explained. I can relate plate tectonics to the formation of crustal features. Today, we're going to complete a plate tectonic boundary note-taking worksheet during the Google Slide presentation. And I will pull that up and show you what it looks like. So as I narrate through the Google Slides, you're going to fill in the blanks during the Google Slide. And it's about 2 pages. Earth's surface is made up of moving solid pieces called tectonic plates. Some of these plates are moving towards each other, some are moving apart, and some are sliding past each other. Plate tectonics is the study of the crustal formations at these plates. The lower part of the mantle is called the asthenosphere. So here, this lower part of the mantle is the asthenosphere. This layer has a similar composition to the upper mantle, but it's partially melted. This makes the asthenosphere like a very thick liquid. And as you're filling in your note-taking worksheet, the blanks are highlighted and underlined. The liquid property of the asthenosphere allows it to flow very slowly. You can think of the lithosphere plates as floating on top of the asthenosphere. So here is your lithosphere. Think of it as the crust, the ocean, and the continents. And your asthenosphere is that top part of the mantle. So the lithosphere floats on top of the asthenosphere. The heat from inside the Earth causes convection currents to form in the asthenosphere. Where the convection currents rise, new material, magma, forces the plates apart. So you see here as the hot material rises and it travels across, it starts to cool, it becomes dense and sinks and rises again. Where the convection currents rise, new material, magma, forces the plates apart. Where the convection currents are sinking, the plates are moving together.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in 2 directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption.
These convection currents in the mantle drag and pull the lithospheric plates above them. Oceanic crust. It's mostly basalt, fast cooling rate. It's new crust, younger rock layers. It's formed at mid-ocean ridges. It's thin and dense. Continental crust is mostly granite, slow cooling rate. It's old crust. It sits on top of the oceanic crust. It's thick and less dense. The majority of earthquakes and volcanoes are found in belts that occur along plate boundaries, where the plates are moving. An example would be the Ring of Fire in the Pacific Ocean. This is where we have lots of earthquakes and volcanoes.
In 1977, two scientists published the most complete picture of the ocean floor that had ever been created, revolutionizing our understanding of the Earth. Named the Tharp-Heezen map after its collaborators, this illustration was produced using sonar and measurements of the water's depth. It revealed, for the first time, a complex network of underwater mountains and ridges, and provided key evidence that supported the emerging geological theory of plate tectonics. This theory states that the Earth's solid outer shell, the lithosphere, is broken into plates. These plates shift and slide over the asthenosphere, the molten upper portion of the mantle. Oceanic and continental plates meet and interact at boundaries that crisscross our planet. Because 71% of the Earth is covered with water, the majority of boundaries are found on the seafloor. When two oceanic plates tear apart from each other at a divergent plate boundary, the space between the divergent plates fills with magma that hardens when exposed to cold seawater. Over millions of years, this process has built chains of underwater volcanoes and rift valleys called the mid-ocean ridge.
When the plates move apart, they rip open the Earth. The mid-ocean ridge, which runs around our planet like the seam on a baseball, where the Earth creates its outer skin. And as these plates move, they're in a synchronized ballet.
There are few places on Earth where the mid-oceanic ridge rises out of the ocean, giving us a chance to see this phenomenon on dry land. Iceland is one of them. The island of Iceland was once an underwater section of the mid-ocean ridge. Over millions of years, it was pushed up above sea level by a giant volcanic hotspot. Here, we can see a divergent plate boundary, a stretch of the mid-Atlantic ridge where the North American and Eurasian plates are spreading or rifting apart. Geologist and oceanographer Dr. Bob Ballard has come to this unique spot where crystal clear glacier water has filled a section of the mid-ocean ridge that has been raised above sea level.
Boy, that's truly amazing. I'm literally at the boundary of creation in Iceland. On my left is the North American plate right here. I can put my hand on North America. I can reach over here and put my hand on the Eurasian plate. And this is the very spot where the Earth is spreading open, about an inch a year, about your height in your lifetime.
When two plates are spreading apart in one section of the world, other plates are moving toward each other in a different area, forming a convergent plate boundary. At these kinds of plate boundaries, one plate can slide underneath the other in a process called subduction. Or, the two plates can crash into each other, creating a mountain range. The Himalayan mountains formed this way when two continental plates collided. On the Mediterranean island of Cyprus, we find an example of a convergent plate boundary that was raised above sea level 90 million years ago as the African and Eurasian plates collided. Dr. Ballard has come to explore this unique part of the mid-ocean ridge in the light of day.
I'm standing on what was an ancient ocean floor, would have been thousands of feet beneath the sea. What we're looking at is an area where the subsequent collision of these great plates, the African plate and the Eurasian plate, and the forces part of the ocean floor up to where it is.
This upward movement revealed ancient volcanic activity that had taken place on the ocean floor.
If you look into that upper section, you can see these round-looking objects. Those are actually what we call the pillow lavas, because as the lava comes out, and no sooner does it come out, it's quenched. And then it expands and continues to quench and forms these pillow-shaped forms, and then it will pop out. You can literally see all these different areas in which the molten lava actually expanded out.
The study of plate tectonics, from the tallest mountains to the bottom of the ocean, helps scientists understand the extraordinary processes that continually shape and reshape our planet, sculpting majestic landscapes, causing earthquakes and volcanoes, and supplying natural resources.
There are three types of plate boundaries. We're going to discuss divergent plate boundary first. This is where two plates are moving apart at spreading centers of the ocean floor. New crust is formed. These boundaries form mid-ocean ridges, such as underwater mountain ranges. Between the peaks of the ridges are valleys called rift valleys on continental crust. Okay, so on the ocean floor you have divergent boundary, magma comes up and new crust is formed. Where we have a continental plate diverging, you have a big crack in the continent, and that is called a rift valley. Convergent boundary will be the second type. This is where plates are moving towards each other. So if we talk about a continental crust coming towards each other, so that's land and land crust coming towards each other, you have a collision zone. Mountains, folded mountains are formed here, like the Himalayas. If we have oceanic crust and continental crust converging, this is where an oceanic plate moves under a continental plate and sinks into the mantle as the plates converge. The action of the denser oceanic plate sinking under is referred to as subduction. Crust is being destroyed. Trenches, volcanoes, and mountains are formed here. So at this convergent boundary, you have an oceanic converging with a continental. Oceanic is more dense, it's more heavy, so it subducts. It goes underneath the continental plate. This part of the plate melts and pushes magma up, forming volcanic mountains along the continent. So we want to talk about the type of crusts that are converging. Here we have an oceanic crust and an oceanic crust converging. This is where one oceanic plate subducts under another oceanic plate as they converge. Because the oceanic crust is denser than the continental crust, the oceanic crust will always subduct underneath the continent. So when we talk about oceanic, what we have here is an oceanic subducting under another oceanic plate. The more dense oceanic, which would be the older one, will subduct. It will go under the less dense oceanic plate. And what we get here are trenches forming in the ocean, as well as island arcs forming in the ocean, volcanic island arcs. So we have volcanic island arcs, volcanoes, and trenches forming where an oceanic converges with an oceanic. Now we're going to talk about another type of plate boundary. It's the transform plate boundary. This is where two plates are sliding past each other. The sliding motion often causes earthquakes. In fact, earthquakes occur at all three boundaries. This happens along faults, so the crustal formation would be a fault that forms at a transform boundary. A fault is nothing more than a crack in Earth's crust where movement has occurred. Crust is not being created or destroyed at a transform boundary where they slide past each other. So the North American plate and the Pacific plate are sliding past each other along the San Andreas Fault in California. Hotspots. Major regions of volcanic activity in the interior of plates away from plate boundaries. So hotspots are these major regions of volcanic activity in the interior of plates. They're away from plate boundaries. The cause is thought to be plumes of magma rising up from the mantle, producing sites of active volcanism. So here you would have a hot spot, it's away from a plate boundary, and it is plumes of magma rising up and forming these volcanic islands. As the plates move over the hot spot, a chain of volcanic mountains form like the Hawaiian Islands. So the Hawaiian Islands form over hot spots. It is not a plate boundary. The plates move over the hot spot, forming these islands.